Hello, we continue our treatment of intensity, and in this set of slides I focus on how to visualize intensity. In particular, we discuss the notion of spatial heterogeneity and the heat map or the kernel density function, which many of you might already be familiar with. So the assumption that we've used so far, and specifically in the homogeneous planar Poisson process, which was the formal expression of complete spatial randomness, we took the assumption of spatial homogeneity. What does that mean? That means that the intensity is the same everywhere. So if we express the intensity at a given location S as lambda S, then in essence spatial homogeneity means that lambda S equals the same lambda no matter where you are. That is the fundamental assumption behind a Poisson process, so homogeneity. Of course, if that's not the case, then we have spatial heterogeneity. And in that case, the intensity lambda S does vary with location S. And so if it varies with location, how do we figure out what the intensity is, right? So we can use tricks like quadrat counts, which we won't discuss here, but in essence it means that it's cuts up the area in different squares and figures out the intensity in each of these squares. It's actually very similar in spirit to what we did for the probability map. So if you recall, one of the interpretations of the probability map is that an indication of potential spatial heterogeneity is that, namely, the intensity is not constant over space. So if it's not constant, how do we estimate it? There are many different parametric models or parametric functions, which means that the function lambda S as a function of S is a fully specified function with parameters. And an easy example is what we call a Trent surface, where the intensity lambda S is simply a function, linear or quadratic function, of the coordinates in space. So as you move further to the right and further up, the intensity increases, for example. That's a very simple parametric specification of a heterogeneous intensity. For exploratory purposes, we typically stay away from specifying models with parameters, and instead we can use a non-parametric approach, which is a kernel function, also known as a heat map. And a kernel function may be a little difficult to comprehend, but it's actually a very simple idea. But before we get into that specifically, is a very important notion, the notion of apparent versus true contagion. And it's all related to the possible existence of spatial heterogeneity, because clustering could be the evidence of more points being in an area than the null hypothesis of CSR would suggest. But it could also be that there's more points in an area because the intensity in that area is higher due to different factors. For example, if you look at COVID cases, you could have more COVID cases in an area because there's a lot of infection, or you could also have more COVID in an area because the intensity is higher because, say, people live in close quarters, so the infection rate is much higher than elsewhere. So in the first case, the infection rate is the same, but we see clusters because people infect each other. In the second case, we see clusters because the infection rate is different. That's the difference between apparent and true contagion. The bottom line is that in a cross-section, we are not in a position to distinguish one from another. So this relates back to this notion I mentioned the other day, that in an exploratory analysis we do not, or we cannot, concern ourselves with the actual process that leads to the particular pattern. We observe a pattern. We observe a pattern of a cluster. That cluster could be due to contagion, which is typically the interpretation, but not always the correct one. But it also could be due to heterogeneity, so a different intensity at that location. So evidence of clustering or clusters may be due to ignoring spatial heterogeneity. So an important aspect of exploring the spatial patterns is to get some kind of measure or visualization of how the intensity might change across locations. And here we make a distinction, but it's actually not a very useful distinction, between an intensity function and a density function. So in essence, they're the same, but they differ by a constant of proportionality. So an intensity function is the expected number of events per unit area. We've seen that before. And if you add it all up, it scales to the overall mean number of events, as it should. Whereas a density function is standardized so that it scales up to 1, like any probability function. And so rather than giving the expected number of events, it gives the probability of an event at a given location. So they're very related. They essentially have the same shape, but one is a rescaled form of the other. And in the literature, they're often confused and used interchangeably. But to be precise, intensity is about the number of events, and density is about the probability of an event. So then that leads us to the kernel density estimation. How do we get some kind of estimate of the possible varying intensity of the process over space? It's non-parametric. There's no, fancy model involved. It's in essence a moving window over the data. And here's the expression. It may look a little formidable, but think of it as being centered on a given location, U, and we are summing what happens at other location, U sub I, but we actually don't sum all of them. In practice, we only sum those that are within a bandwidth distance from the point U. So this little expression in the brackets here is the distance between U and each of these other points, U sub I, as a fraction of the bandwidth. So that can go from very small, very close to 0 for points that are very close to U, to around 1 for points that are exactly one bandwidth away from U. And so what do we do with this fraction? This is a fraction. We plug it into this function. And this function, in essence, weighs each of these distances differently. So the easiest kernel function is a disk function, which doesn't do anything. It just would count the number of points that are within the bandwidth. That is a very simple kernel function. So then you have this expression, you rescale it by the number of points just to, end up with a comparable magnitude. Remember our discussion of the distinction between intensity and density. They're basically the same, but rescaled by a factor of proportionality. So for each point U, we can compute this and then we graph it. And just to make it concrete, let's say this example is I like it a lot. It comes out of the CrimeStat manual. CrimeStat is another package to analyze particularly patterns of crimes, but it's any kind of event. So let's see, we have a point here, point 7, and we fit this kernel function over it, this kernel over it. And so we take the distance between 7 and 8, plug it into the function. Distance between 7 and 9, plug it into the function. Distance between 7 and 12, and plug it into the function. And we add them all up, and that is the value of the kernel function for 7. So then for 8, we do the same thing. This is our kernel function for 8. We take the distance to 7, plug it in here. Where are we? No, plug it in here. We take the distance to 9, plug it in here. Distance to 12, plug it in here. And then that gives us the value for 8. And same for all these other points. So we do this in principle, for every location along the line. In practice, only for the data points. And then we get this nice smooth curve. And to show you the effect of the bandwidth, we'll do this again for a much narrower bandwidth. So you see the same little kernel functions, like the one above 8, is now much narrower. It doesn't take 0.12 into account at all, so the resulting density estimate is much sharper, much spikier, as I like to call it. So that's the principle of a kernel density function. You can think of it as a window average that assigns the value, the sum of the events in the window to the point at which the window is centered. In the simplest kernel function, the disk function, there is no weighting, but all the other ones, like the one we see here, you see that this is plugged into this function to give it a weight, and then all these weights are added up to assign a value to the given point of reference. That's how it works. So let's see some specific examples and what they look like for our example, for our Chicago supermarket example. In the point pattern literature, the Gaussian kernel function is used a lot. And it's also the example you saw in the previous slide. You see the bell curves here. These are the kernels. And then the resulting kernel density estimate is the blue line. So in this case, the kernel function, the red curve, is a normal distribution or Gaussian distribution. The important parameter is this b. B is the bandwidth, which corresponds to the standard deviation of the distribution. So smaller bandwidth, a smaller standard deviation, is a spikier kernel. Larger bandwidth is a flatter kernel and a broader range. And so the bottom line question is, what should the bandwidth be? And this is actually a topic of a lot of discussion. There is a literature on determining optimal bandwidths. Depends on the assumptions you're willing to make. You can do try a bunch of different values and pick the one with the smallest mean square error. You can use a probabilistic approach and pick the one that yields the highest likelihood. You can do an ad hoc procedure and just kind of look at the distribution of the distances and then pick a quartile or a quantile in the distance distribution. So you look at all the distances and say pick 20% or 25% or 10% and just kind of see what it matters. The important thing to realize is that more than the kernel function, the bandwidth selection matters in terms of the impression that you get. One approach is the one that I like to take, is just not to get hung up on this optimal bandwidth too much, but just to try a number of different values and assess the extent to which it changes your impression of the patterning in the data in more of an exploratory fashion, more of a sensitivity analysis approach. You pick different bandwidths and see the effect of that. And let me illustrate that for our Chicago supermarket example. So this is a Gaussian kernel. The bandwidth is the optimal one that SpatStat picked. The darker areas are lower intensity, and you see this is the southern area, and then obviously we already know this, O'Hare doesn't have any supermarkets. And then the high intensity areas are all in the north, downtown and north of the loop here, right? So now let's say we will make the bandwidth much smaller. Before I show you the slide, think about this for a second. What do you think is going to happen? So this is the same as what I illustrated before. We had our bell shape, and now the bell shape is much narrower. What is going to happen? Just keep in mind, the kernel is actually a smoothing of a window. So you can think of a circle around these points, and it's counting the points in the circle. So we're making the circle smaller. What does that do? Much more dark colors. Why? Because the bandwidth is much smaller, so you have the circle around these points, and they might very well not count any others or very few others, so they get much darker. So the area of high intensity shrinks to just the loop and the area immediately outside the loop, and then we have two kind of branching out areas that are not quite as bad, but then the dark blue area is much larger relative to the larger bandwidth. So this illustrates the importance, or I should say the sensitivity of the result of a kernel density map, or a heat map if you prefer to call it that, to the selection of the bandwidth. And then to show you the other aspect is the choice of the kernel function. I already mentioned the uniform or disk one, which is simply counting the points within the bandwidth. Another common one is a triangle one. You can think of it as a kernel function like this. Remember, we had the bell shape. Now we go with the triangle, which is z is a fraction. It's the fraction of the distance to the point over the bandwidth. So it's 1 minus z. So as z increases, this number gets smaller and smaller. It's linear, it's a triangle, so when you hit the bandwidth, z is 1, and so this is 0. So then it stops. Epinechnikov is a similar idea. It's 1, but it penalizes the distance double. So it's a square of this fraction. Again, when z is 1, it stops. So it stops at the bandwidth. And then the quartic kernel function is a double square. So this is the same as Epinechnikov, but then it gets squared again. So it becomes even smaller, because remember, these are fractions. So 1 minus a fraction is a fraction. And here we take this fraction and we square it, so it becomes still smaller. So that's a much higher penalty for points that are further away. It drops off much quicker with the quartic kernel function. And to show you the effect of the choice of the kernel function on the heat map, we don't change the bandwidth. So we use the same bandwidth as we did in the original example for the Gaussian. So, if we go back real quick, this was the Gaussian example with this bandwidth. And so now we go uniform, pretty much the same. This is dark blue, this is dark blue. All the yellow is up here. Epinechnikov, quartic. I bet you can hardly tell the difference between them. Of course, there are differences, but the bottom line, the main point, is that the choice of the kernel function itself is not that critical. The choice of the bandwidth makes all the difference in the world. So this concludes our discussion of intensity of point partons. So we saw how we measure it, how it is affected by the size of the bounding polygon, how it is used as an average, as the mean of a Poisson process in formalizing a spatial random distribution. And then in this set of lectures, we visited the notion of spatial heterogeneity, where now the intensity is no longer necessarily constant throughout the space, but is allowed to vary. And one way to assess that, the extent to which it varies, is by means of a non-parametric kernel density function. We saw a number of different density functions, Gaussian, disk, triangular, etc. But the main point is that the bandwidth determines the shape of the heat map, the shape of the impression of the spatial distribution. So next lecture will go into nearest neighbor distances and distance statistics. See you then. Bye.